Good morning. So if you haven't met me yet, I'm Sean, and I primarily work on photovoltaic materials and or emerging photovoltaic materials, and that's kind of my focus in the group. So following on from a fantastic intro to electronic structure theory last week from Chris, today we're going to look at how these material properties relate to solar cell operation. So firstly, what goes in a solar cell? So in the middle, you've got an absorber material, so which makes up typically the bulk of the solar cell, which you guessed it, absorbs sunlight and converts it to mobile electric charge or electric current. And usually this is interfaced with another semiconductor, so in this case, cadmium sulfide, so a thin layer here, which may or may not be made of the same material to form a PN junction, which aids in the charge separation and thus generation of an electric current. You then have contacting materials above and below, which connect the PN junction to an electric circuit or an external electric circuit. Importantly, the top one of these contacting materials has to be transparent to allow light through so that it can be absorbed. And so these are known as transparent conducting materials, which are another important research area with major technological applications, so touchscreens and transparent electronics, which other people in the group are looking at. And we'll be getting a tutorial on these from Joe next week. So anyway, these components are of course very important to solar cell performance. However, these days it's often just an engineering issue to optimize these components for our given absorber material, which is in fact kind of the bread and butter or the performance defining ingredient of the device. So the photovoltaic effect, which is the principle upon which the vast majority of solar cells are based on, is defined as the generation of voltage and electric current in a material upon exposure to light. So this is what we call solar photovoltaic devices are based on. So these are our solar cells. So basically we have some form of energy gap for the electrons in our materials. So they can occupy states at this energy, but then there are no electronic states that can be occupied for a certain range up to what we call our conduction band here. And so a photon comes in, hits an electron, which can then absorb the energy of the photon to cross this forbidden energy gap and occupy a higher energy electronic state. So then the next step in a solar cell is to then use this excited mobile charge carrier to generate electric current. And so to do this, they must be separated. So we must separate the excited electron and the positive hole that it left behind. And so this is typically achieved using the PN junction you saw in the 2 slides previous. So this is the concept upon which the vast majority of solar cell devices are based on. And so just to mention, the other solar technology that exists is something called CSP, so concentrated solar power, which works on the principle of converting light to heat to steam, which is then used to power a turbine engine, like in coal or a lot of nuclear plants. So given that we're absorbing light energy by exciting electrons, the arrangement and behavior of electronic states in our absorber material, so aka the electronic structure, is paramount to performance. So while there are a variety of flavors of solar cells, essentially based on different ways of forming an energy gap. So for example, in organic solar cells, which are basically composed of molecules, the energy gap arises from the HOMO-LUMO gap, so the highest occupied molecular orbital to the lowest unoccupied molecular orbital, or in quantum dot solar cells, for example, quantum confinement is leveraged to kind of generate or tune an energy gap in these materials. However, in this group, we primarily look at solid inorganic semiconductor absorber materials. And why? Well, they generally give the best mix of efficiency and scalable fabrication techniques. So if you recall from last week, in a semiconductor, we have what we call the valence band. So a energy range at which we have many occupied electronic states. Then a energy gap where there are no available electronic states. And then above this, a conduction band. So where there, again, an energy range of electronic states, but that are at equilibrium unoccupied. And so this is what we call the band gap, the forbidden energy gap between the valence band and the conduction band. So this is kind of a simplified picture of the density of states, and in a real material, it looks something kind of more like this. So a few more features and peaks, but the general concept remains. So you have your occupied valence band states, some energy range where there are 0 electronic states that we can occupy, and then above this, the conduction band. So one of the main ways we analyze electronic behavior in semiconductors is through the band structure. And so Chris gave a fantastic introduction, obviously, last week to this. So just to give a brief recap of what a band structure is. In a solid crystalline material, because we have a periodically repeated atomic unit cell, the electronic band states themselves are periodic waves or wave functions. And so the energies of these wave states will depend on the phase of the waves, so whether it's low frequency or high frequency. Or another way of thinking about this is the interaction of atomic-like orbitals between different unit cells, which make up the overall wave states. So different wave phases correspond to different points in reciprocal space. So you can think about it in either way here. So a different, the different reciprocal space points correspond to different wave phases, which we call K points. So a band structure is then simply a graph of the variation in energy as we move between different points in reciprocal space, so as the wave phase changes. And we have certain labels for special or high symmetry K points, which occur on our Brillouin zone, which is the unit cell or the unit cell in reciprocal space. So a key question is, what is the ideal energy gap for the maximum efficiency in our solar cell? So in 1961, Shockley-Quiesser made a pretty good stab at this, deriving what we call the Shockley-Quiesser limit for solar cell efficiency for a given band gap energy. So if you plot the maximum efficiency or the fundamental limit to the maximum efficiency versus the band gap, they found that you get this sort of shape with a sort of Goldilocks type zone between 1 and 1.6, 1.7 electron volts, where you can attain solar cell efficiencies greater than 30%. And so the question of why we get this sort of shape can be understood if you think about essentially what happens when photons come into our device. So when photons come in from the sun and hit an electron in our valence band, if the photon has an energy greater than the band gap energy, it will excite the electron up into the conduction band. If the photon energy is much larger than, or significantly larger than, the band gap energy, it will excite the electron up even higher than, say, the bottom of the conduction band, which will then rapidly decay down to the conduction band edge in a process that we call thermalization. So this is where the electron is giving off its excess energy as heat, so through lattice vibrations that we call phonons. And this typically happens much more rapidly, much quicker than we can extract these electrons. So generally this happens before we can then extract the electrons and use their energy to create electricity. And then likewise, if the photon has an energy less than the band gap, there are no electronic states that we can excite to. So because there's no electronic states at any point along here, if the photon has an energy less than the band gap, it can't be used to excite our electrons. And so it essentially just passes through the device and isn't absorbed. So if we had a device with a very low band gap energy, we'd get a huge amount of absorption, because we'd absorb most of the photons coming in from the sun, because most of the photons would have the energy greater than our relatively small band gap. But we would also be losing quite a lot of energy due to thermalization, because all our higher energy photons that excite electrons way above the conduction band edge are then losing energy due to this thermalization process. And then likewise, if we had a very high band gap energy, we would miss a lot of the photons, so we get much lower absorption, but the actual energy that we can extract per photon that is absorbed is much higher, because our energy gap is much higher, and we get a kind of larger amount of energy per absorbed photon. And so given the shape of the solar spectrum, so the kind of distribution of energy of the distribution of photon energies from the sun, we end up with this Goldilocks zone around here, which gives us the ideal band gap for an efficient solar cell material. So this model gives us a very useful picture of the upper limit of device efficiency based on the fundamental band gap of the absorber. In reality, it is a highly idealized model, so involves a number of unrealistic approximations, such as perfect absorption above the band gap, an ideal charge carrier collection, so no non-radiative recombination of electrons and holes before extraction, zero resistance at the device interfaces, etc. But it is, as I said, a very useful model for kind of looking or being able to predict an upper limit to efficiency straight from the band gap energy. So second to the band gap energy, the next material property to determine the maximum photovoltaic efficiency is the absorption spectrum, which itself arises from the electronic structure. Wrong direction. There we go. So depending on the orbitals involved in the band edge states, our conduction band minimum, or CBM, and valence band maximum, VBM, can arise in different points in reciprocal space. So usually, but not always, the CBM and VBM will occur at one of the high symmetry or special K points in our in reciprocal space, or on our balloon zone. So because photons have near zero momentum, certainly relative to electrons, which would correspond to changes in reciprocal coordinates for our electrons, kind of like a horizontal transition, electrons can only undergo directly vertical transitions just with photon absorption. So when an electron is struck by a photon, it can provide the energy, but will provide no momentum change. So this means if we have a direct gap semiconductor where CBM and VBM occur at the same point in reciprocal space, we will typically get strong absorption at the band edges, because once we have photons coming in at an energy equal to or greater than the band gap energy, we can immediately excite electrons from our valence band to the conduction band. However, if we have an indirect gap, to do this sort of diagonal transition from our VBM to a CBM located at a different point in reciprocal space, the electron needs to absorb both a photon to provide the kind of upwards energy shift, but also a phonon, or a lattice vibration, to provide this momentum change or horizontal shift from X to L here. So we call this a phonon-assisted transition, which is required to conserve momentum in the material. So beyond the magnitude of the band gap, this is probably the next most important feature in the band structure of a potential photovoltaic absorber, as it has important implications for the absorption behavior. So with the direct gap semiconductor, we typically get an absorption spectrum like this, where you have a characteristic sharp onset and absorption once the energy reaches the band gap energy. However, for an indirect gap semiconductor, where we have to rely on this phonon assisted transition, we actually get a weak onset and absorption at the band gap energy, because the probability of having both a photon and a phonon available at the same time to undergo this transition is much lower. And then once we have enough energy where the electrons can undergo a vertical transition, so for example, going from here to here, once the photons are high enough in energy to allow us to make this transition, we then often see this kind of upshift in absorption or a sharp onset once again when we can do these vertical band-to-band transitions. So typically we don't want this for solar cell applications because direct gap semiconductors can use thin films in solar cells. So you only need a kind of relatively thin material to absorb most or all of the solar spectrum. Whereas for the indirect materials, you need a much thicker film to ensure that you're getting, they're absorbing most of the photons coming in. So this is what silicon solar cells are based on. And so why we don't want this, well, there are kind of many reasons, but the big ones would be firstly cost. So if you have a thicker device, just means it costs more to make it because there's more of the material there. But also having a thinner device can help charge carrier collection and efficiency. So there's less volume for impurities and electron hole recombination. You usually have more flexibility in terms of synthesis and device architectures. And also they're just lightweight and easier to install and kind of more flashy. However, the optical behavior will depend on much more than just the direct versus indirect nature of the band gap. So one of the fundamental truths in life is that if you ever quote David a band gap, he will immediately ask whether that's the optical or the fundamental gap. So what is he talking about here? So many experimental techniques determine the band gap using optical absorption techniques, or techniques that at least rely on the optical absorption of the material. So such as UV vis absorption or photoconductivity measurements, etc. And these can actually give you a different energy gap to the actual fundamental gap in the material. So we're defining our fundamental gap as the difference in energy between the CBM and the VBM. So one way this can arise is if you have strongly bound excitons in your material. So an exciton is kind of a electron hole pair that is bound by the Coulomb attraction, or the charge attraction between the negatively charged electron and a positively charged hole that it left behind in the valence band. And so because of this attraction between the electron and the hole, you get a lowering in energy. And so you end up with a state that is actually lower in energy than, say, your conduction band minimum. And so you'll, if these species exist in your material, you will often measure an energy gap which is lower in energy than the fundamental gap. So this, which we call the optical gap, because this is what is measured by the optical techniques. So large excitonic binding energy, so this difference between the energy gap and the optical, or sorry, the fundamental gap and the optical gap, can occur for localized electronic states. So as opposed to delocalized electronic states where the electrons are spread across thousands of atoms, whereas if they're kind of more localized in space, spread out only over a couple of atoms, you can have a much stronger interaction between the electron and the hole. So looking at a band structure and how this kind of translates to a band structure, a general rule of thumb is that if you have a localized or electronic states that are localized in energy, so where the band, as you move across reciprocal space, only occupies a small kind of energy range, this typically corresponds to localization in real space. So flat bands generally mean that you have a corresponding to electronic states that are quite localized. And so, for example, this would be like s orbitals with small overlap and interaction between the different orbitals involved. So there are various ways to calculate the exciton binding energy at varying levels of theory. So kind of a crude way is just to use the effective mass from your band structure. So just by looking at the dispersion at the band edges, you can get a estimate of the exciton binding energies, or you can go all the way up to very exotic techniques such as GW plus BSE, the Bezier-Salpeter equation, depending on how important this behavior is in your material. Another way that the difference in fundamental and optical gap can occur is through symmetry forbidden transitions. So if you recall from undergraduate spectroscopy courses, we have certain selection rules for optical transitions, and as a result, certain vertical electronic transitions can often be symmetry forbidden. So this here, the transition dipole moment, is one of the determining factors in the rate of electronic transition. So for this integral to be greater than 0, and so to allow a transition, the change in spin must be 0 and the change in parity must not be 0, because so the dipole operator here, mu, is odd. So if we have an even by odd by even, that will give us an odd output, and then so the integral of an odd function goes to 0. So for this not to happen, we need to have some sort of difference in parity between phi 1 and phi 2, so that we end up with an integral that is greater than 0. So for this parity selection rule, so the Laporte selection rule, to apply in a crystal, you need to have an inversion center in the crystal structure, which corresponds to having a centrosymmetric space group. So in this case, if you have, for example, a Gerada symmetry valence band, so the G for Gerada, which is even symmetry, and also a Gerada even symmetry conduction band minimum, we will have very weak, or formally 0 absorption between these two band states, because it's symmetry forbidden. So in a real material, this will be slightly broken by things like vibrations, small distortions, spin orbit coupling, etc., which will kind of distort the symmetry slightly of these states and allow some form of absorption and transitions between them, but it will be extremely weak. And so if you look at kind of this on an absorption spectrum plot, you see that you'll get very low or kind of negligible absorption at these energies just above the band gap, until at this higher energy here, you suddenly can transition between a state of ungerada symmetry to gerada, so odd to even, and then you'll get kind of your onset and absorption at this energy. So again, this could be quite bad for solar cell performance, because your energy gap is much larger than your fundamental, and so you'll end up missing quite a lot of photons due to poor absorption, and then also losing a lot of energy due to thermalization when you do absorb the higher energy photons. Okay. So this sort of behavior is very important to keep in mind when comparing to experiment, and also thinking about potential solar cell performance. Because what you can have in certain situations is what some people would call a where the optics look great. So the experiment gives you a band gap at 1.5 electron volts, which sounds great, but then the fundamental just doesn't really cut it. So the fundamental might be down at half an electron volt or 1 electron volt, and so it actually turns out to be quite bad for solar cell performance. So with these considerations in mind, we need to move beyond the Shockley-Quiesser model to get a realistic picture of the potential solar cell efficiency for a given material. So perhaps the first major extension of this model is the SLME, so the spectroscopic limited maximal efficiency, developed by Ewan Zunger nearly 10 years ago. And evidently, so what this model does is it's essentially the Shockley-Quiesser model, but incorporating the effects of imperfect finite absorption. So removing the assumption of perfect kind of step function like absorption, which the Shockley-Quiesser model uses, and then accounting for the actual absorption spectrum of our material. So as you can see here, where we plot the SLME versus the Shockley-Quiesser limit, it can significantly affect the estimate of the upper limit to efficiency for our materials, dropping down slightly in each case. This is also now available as a PyMatGen Python module, which makes the calculation much less painful. And there are further more accurate methods to estimate the maximum photovoltaic efficiency, such as the Blank et al. Method, which also accounts for slightly more exotic effects like light outcoupling and photon recycling. Sung-Young Kim's trap limited conversion efficiency, which takes defect mediated non-radiative recombination into account. However, this of course requires that you've calculated the defects in your system. So if you're reading papers or talking to engineers or experimentalists working on actual device fabrication, you'll hear the terms open circuit voltage, short circuit current, and fill factor quite often. So what do these terms mean, and how do they correspond to our calculated material properties? So they all refer to different things on an electrical engineer's favorite graph, the JV curve. So firstly, the open circuit voltage, VOC, here is the voltage or potential difference across the cell when no current is flowing, and corresponds to the maximum voltage available from the solar cell. So ideally, this would equal the band gap, as this is the difference in potential between our excited electrons and the valence band. However, the open circuit voltage is always slightly lower than the band gap, primarily due to electron and hole recombination, whether radiatively or to emit photons, or non-radiatively to emit heat or phonons, which can happen at defects and grain boundaries. The short circuit current is the current, so the short circuit current is the current through the solar cell when there is zero voltage across the cell. And so this corresponds to zero resistance to the flow of electrons. And so this current density is determined by the number of conduction electrons and holes available, which itself corresponds to the number of photons absorbed, because we get essentially one electron hole pair for each photon absorbed approximately. So the and the electrical power in a device is given by this formula here. So power is equal to current times voltage, or P is equal to IV. And so we define the fill factor as the ratio of the maximum power output of the solar cell, corresponding to the area of this yellow square here. So operating at the voltage and current, which gives us this maximum kind of square area, so our maximum output power, to the product of the open circuit voltage and the short circuit current, so this larger square here. So the fill factor is just a ratio of the area of this square to the larger square here. So essentially it's a kind of measure of the squareness of our JV curve, which looks like if you know what the JV curve for a diode looks like. And so its value primarily depends on recombination and resistance at material junctions in the solar cell. So this graph here kind of gives a nice illustration how all these terms depend on the band gap energy. It's a bit messy, but so essentially as our band gap energy increases, the open circuit voltage will increase, because again, we're increasing that potential difference between our excited electrons and the valence band. However, the short circuit current will decrease because, again, as we're increasing our band gap energy, we're absorbing less photons, and so there's less electron hole pairs being generated. It's just that each electron hole pair that we do generate is now at a higher energy and higher voltage than if it was lower energy or lower energy gap. And then the fill factor slightly increases as the band gap energy increases, because the kind of reduction in area due to the roundedness of our JEV curve becomes less significant as the voltage increases. So to wrap up, there's a long list of desirable features for an ideal photovoltaic material. So we looked at kind of the factors that affect efficiency, such as band gap and absorption. We also, many other factors affect this, such as defects, exciton separation, your charge carrier mobilities, etc. Beyond that, you would ideally want your solar cell to be made of cheap and abundant materials. So it's no good if you can make a highly efficient solar cell out of platinum or something, for example. You want it to be relatively cheap materials that you can scale up. You want them to be stable, so for them to last long enough, non-toxic, and also scalable or kind of industrial scale fabrication techniques. So it wouldn't be a proper solar panels talk without showing this figure. So if you do end up working on solar cells, be aware that you'll probably be shown this chart at, like, you know, every opening conference talk. So making the perfect solar cell is kind of like engineering a championship winning Formula One car. So you need to get the basics right first. So good absorption properties, stability, abundant non-toxic materials. Just like, you know, getting your tires wrong means you'll crash out before you can even finish the race. But from there, it takes a lot of money and research and development to fine-tune the device or car performance, like getting the contact materials right, your ideal doping strategies, reducing charge carrier losses, junction resistances, etc., all of which contribute to these incremental increases in efficiency over the years. So that's that's it, me finished. So thanks for listening, and thanks for your attention.